Welcome everybody to Algebra 2, Section 9.3, Sample Spaces, Theoretical Experimental Probability, and Counting Techniques. So probability is defined as the likelihood of an event occurring. And I want to note that it is always going to be a number between 0 and 1, aka 0% to 100%. Outcomes is the result or are the result of an experiment. An event is any set of outcomes and then sample space is going to be all possible outcomes of an experiment. I'll talk about these as we use them a bit. So an example, in an experiment, 3 coins are flipped. List the possible outcomes in the sample space of the experiment. So the event is that coins are flipped. So when a coin's flipped, you can either have heads or tails. Now, the sample space with 3 different coins being flipped, like let's say you get all of them are heads. You could also have the first 2 are heads and the last one's tails. And maybe the second one's tails, but the other 2 are heads. And maybe the last 2 are tails. Okay, well then you could also have that maybe all 3 of them are tails. Or maybe the first 2 are. Or the first and the last are tails. Or just the first one's tails. And these are all technically different scenarios that would happen. And so there's a total of 8 different outcomes in our sample space. So each of these is an outcome, and they all make up the sample space. So these are all the possible outcomes. So how many outcomes are there? There are 8 possible outcomes. And another way you can arrive at that is you can say you have 2 outcomes for the first one, heads or tails, times 2 for the second one, heads or tails, times 2 for the last coin, heads or tails. And just take 2 times 2 times 2, aka 2 to the third power, and you get 8. And once again, that's because you have 2 for each coin flip. So 2 possible outcomes for each event, each coin being flipped. Example 2, you flip a coin, then you roll a 6-sided die. How many possible outcomes are in this sample space? And list them. So possible outcomes, so flip a coin. So you get a half heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. You could also have tails in all of those same numbers. Hope I wrote 2 again. Giving us a total of 12 possible outcomes in our sample space. And another way we could arrive at that is the coin has 2 different options, heads or tails. The die has 6 different options, 1, 2, 3, 4, 5, 6. Multiply 2 times 6. Now let's talk about theoretical probability. Theoretical probability, we're going to say it's P of A is how we say it, probability of event A occurring. So it'll be defined as the number of probable outcomes in event A, such as flipping a coin or rolling a die, divided by the total number of outcomes. And when we talk about theoretical probability, we're saying this is how it should work. Like, for example, if you flip a coin twice, you should get heads once and tails once. But if you flip a coin 2 times, that might not be what happens. So example 3, if you are equally likely to choose a number between 1 and 20, what's the probability that you choose a number divisible by 20? So the probability that you get a number divisible by 5. So we're going to say, well, how many numbers between 1 and 20 are divisible by 5? Well, the sample space is going to be 5, 10, 15, and 20. Those make up the sample space because those are the numbers divisible by 5 that are between 1 and 20. So you have 4 probable outcomes in event A that could happen out of 20 total outcomes, numbers 1 through 20. So that gives us the theoretical probability of 1/5, aka 20%. So 1 out of 5 times you randomly choose a number, then you should get 1 divisible by 5. Meaning the other 4, you should have one that's not divisible by 5. Example 4, if a pair of dice, that should be dice because die is singular, is equally likely to land on each number, so aka it's no more likely to land on a 2 than a 3, what's the probability that the sum is 7? So, probability of a sum of 7, you have a total of 36 different options for for the dice to be rolled. Like we talked about earlier, 6 for the first, 6 for the second, 36 total. Because you could have a 1 and a 2, a 1 and a 3, a 1 and or 1 and a 1, 1 and a 2, 1 and a 3, 1 and a 4. But you could also have a 2 and a 1, a 3 and a 1, a 4 and a 1, and those are technically different because the other dice has the 1 compared to the first set of scenarios. So our sample space here for ones that are going to have a sum of 7 are going to be 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, and 4 and 3, giving us 6 different possible options out of the 36, meaning 1 out of every 6 times you should get a sum of 7. Once again, that's not always going to happen. You can think about how, if you're familiar with the game Monopoly, rolling doubles allows you to go again right away. But if you roll doubles 3 times in a row, then you go to jail without taking your turn. So doubles in Monopoly has a theoretical probability of rolling those 2 dice to get a set of doubles of 1 and 6. But that doesn't mean it's going to happen exactly every 6 rolls, where, it's like, oh, we had 5 rolls that weren't doubles. Here's the 6th one, it's going to be a double. Not how it works, because sometimes you can have doubles 3 times in a row very easily. So experimental probability is the other hand of that, where it's saying, hey, maybe you had doubles 3 times in a row in Monopoly. Well, the theoretical probability, you should only have it 1 out of every 6 times. So it doesn't mean the theoretical probability is wrong, it just means that's how it should work, but it's not how it'll always work. So that'll be experimental probability for us. So using this table and spinner to the right, we're going to find the experimental and theoretical probability of these things. So the theoretical probability, the next spin is blue. So these spinners, 4 even spots of red, yellow, blue, and green. So theoretically speaking, the probability that it'll be blue is 1 out of 4, as even of a chance to the others. What we've seen so far is the experimental probability. It's come up 4 out of a total of, if you add up 10, 2, 4, and 3, 19 times. So it's come up 4 out of 19 times. So less than a fourth of the time is what we've seen in our experiment. Now, it doesn't mean that the spinner is skewed or favoring certain colors or another. It's just how it randomly happened. So what's the theoretical and experimental probability the next spin is green? Go ahead and find that. The theoretical probability the next spin is green is once again 1 in 4, because all of those colors have an even chance. The experimental, though, is 3 out of 19, so quite a bit lower. All right, moving on. We're going to talk about the fundamental counting principle. If there are M, as in Mississippi, outcomes for an event, and a second independent event has N, as in Nebraska, outcomes, then M times N is the total number of outcomes together. So that's actually what we were talking about a moment ago with rolling 2 dice, or flipping 2 coins, or rolling a die and flipping a coin. We're saying, hey, the first one, maybe flipping a coin, has 2 outcomes, heads or tails. The second one, rolling a die, has 6 outcomes, 1, 2, 3, 4, 5, 6. So if you multiply the 2 times the 6, you get 12 total outcomes. And that's our fundamental accounting principle. And we can use that to help us find out how many different possible outcomes there are very quickly. So let's say Jimmy John's has a special. For $6, you can get a turkey or ham sandwich with barbecue, ranch, or plain baked Lay's, and a medium drink. So now there's 4 soft drinks available, and we want to know how many possible different orders are there. So you can do like a tree diagram, for example. You can say, okay, out of your 2 sandwiches, you have turkey and you have ham. And if you pick turkey, you could get 3 different types of chips. You can get barbecue, you can get ranch, or you can get plain. And then you can have those same options for if you pick ham. You can get barbecue, you can get ranch, and you can get plain. So then if you have turkey and you choose barbecue chips, well, you still have those 4 different options of soft drinks. And same thing's true with ranch. You still have those 4 different options. And same thing with plain baked Lay's. You still have those 4 different options. So if you have a turkey sandwich, you have a total of 12 different ways you could go from there. And a ham sandwich, you're going to have the same thing. 4 different soft drinks for the barbecue chips. Well, you could do the same 4 soft drinks for the ranch, and the same 4 soft drinks for the plain. And so you end up having a total of 12 options, whether you choose ham or turkey, for a total of 24 outcomes. Now, that's a lot of work, a lot of drawing, a lot of mapping. What we could do instead is say the first choice you make, turkey or ham sandwich. That's 2 options. The second choice you make, the chips, barbecue, ranch, or plain baked Lay's. That's 3 options. And the third and last choice you make, the drink, 4 soft drinks. So times 4. So you take 2 times 3 times 4, and voila, you get 24. It is much, much quicker. So on this next one, I want you to try the tree diagram and then try the fundamental accounting principle. So suppose your state is adding a new area code. The first digit must be a 5 or 6, and the second digit must be a 2 or 3 or 4. And the third digit must either be a 0 or 1. So you can either start with a 5 or a 6. Then from there, the second digit must be a 2, 3, or 4. So if you start with a 5, you could go to 2, 3, or 4. You can start with 6, you can go with 2, 3, or 4. And then our last one has to be a 0 or 1. 0, 1, 0, 1, 0, 1. So you could have 5, 2, 0, 5, 2, 1, 5, 3, 0, so on and so forth. And same thing, you could have 6, 2, 0, 6, 2, 1, 6, 3, 0, 6, 3, 1, and so on and so forth. And you end up getting a total of 6 plus 6, 12 outcomes. Whereas the other way we could do it is say, okay, the first digit, 2 different options. The second digit, we have 3 different options. And the third digit, you have 2 different options again. So you take 2 times 3 times 2, and you get 12. Once again, much, much quicker. Angela needs to make up a 5-character password for her account on the internet. The password has to consist of 2 letters, followed by 3 numbers. So how many different combinations, different passwords are possible if they can be repeated? So like let's say if you use your first letter, because it has to have 2 letters followed by 3 numbers. So the first 2 have to be letters. So the first letter, let's say you pick A. The second number, you could pick A again. So you have 26 options for your first letter and the same 26 for your second letter because you're not restricted. And then, so that's the 2 letters, and then followed by 3 numbers. So the 3 numbers, well, you have 0 through 9 because you can't really pick 10 because 10 is not a single digit number. So 0 through 9 are 10 different options. If you're struggling with that, count them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 options and 10 options. So you take 26 times 26 times 10 times 10 times 10, and that allows us to use the fundamental counting principle to figure out that there would be, let's say red and blue make purple, 676,000 different passwords. Quite a bit. So if you're just trying to randomly guess someone's, there's not a good chance you'll get it right. Now let's say how many are possible if they cannot be repeated. So let's say you do 26 for your first one, and then for your second one, if you chose A, you can't choose A. So you only have 25 letters. And then your number, you have 10 options. But then the next one, you can't use the same one, so you only have 9. And the third one, you have to use another number, so you're down to 8 options left. So this will see that you only have 468,000 different passwords available. So still quite a bit, but obviously significantly less than 676,000. That's what changes when you're able to repeat a number or a digit versus not. I should have said a letter or a digit because numbers and digits are the same. Factorials. I'll say it's the most exciting thing about math because factorial means there's an exclamation point. It's how we write it out. Now, there used to be 9 teams in Plasmith Conference back when these notes were made, but now there's 8 because we're in a new conference. How many different ways can the teams finish in the conference? Well, first place, 8 different teams can get it. Second place, though, if a team already got first, only 7 teams are left for that. Third place, if a team got first and second, there's 6 teams left. If a team already got first, second, third, there's only 5 teams left for fourth. 4 teams left for third, 3 teams left, 4 teams left for fifth, 3 teams left for sixth, 2 teams left for seventh, and the last team would have to get eighth then. So you take, once again, this was first place down here with 8th place or last place down there. And this would give you the same thing as what we call 8 factorial. 8 factorial is defined as that number times every number before it. So 8 factorial is 8 times 7 and all the way down to 1. Whereas like 20 factorial would be 20 times 19 times 18 times 17 times 16 all the way to 1. And 8 factorial would equal 40,320. Now the nice part about factorial is your calculator can do that for you. Instead of having to type in just 8 times 7 times 6 times 5 times 3 times 2 times 1, you can type in, if you hit 8 and then the math button and go over to probability, and it'll be the 4th option, the exclamation factorial. And if you hit enter, it'll tell you, oh, that's 40,320, like we just said. So that's obviously a lot of different ways that 8 teams could finish in the conference. How many different arrangements of the letters of the alphabet are possible? So if a bag contains 26 tiles, letters A through Z, for each letter of the alphabet, what's the probability that they pull out, or I should have answered this question first, I'm sorry. How many different arrangements of letters in the alphabet are there? It's 26 factorial. So we're talking about arranging everything. It's always going to be that number factorial. So like, how do you order 5 songs in a playlist? 5 factorial. How do you order 20 people in a classroom? 20 factorial. So a bag contains 26 tiles lettered A through Z. What's the probability I pull out 1 letter at a time to create the correct alphabet? Not very likely, okay? Because out of the 26 factorial options, that's why we said how many total there are, we talked about theoretical probability earlier being the number of probable or correct outcomes technically out of the total number of outcomes. So the total number is 26 factorial. So many different combinations you could make of the alphabet. But how many of those are actually the correct alphabet? Well, there's only one correct alphabet, 1 out of over 26 factorial. Well, if we go to our calculator here, we'll figure out that's a very small number. 1 divided by 26 factorial. You can see here that fraction showing just how incredibly small it is. And that's saying 24 times 10 to the negative 28th. So there are going to be 26 zeros before we get to the 2 and the 4 there. So obviously not very likely that you just randomly create the alphabet this way. On to some different examples now. So what happens if there are some things that are repeated? So example 6, how many distinguishable arrangements are there with for the letters of the word free? So free would be different than if, like, let's say you were rearranging the words of, or just 26 different letters in the alphabet because they're all different. So like even if you were to rearrange trip would be just ordering those 1 through 4, just like we did the teams in the conference, 1st through 8th, and all those different things. So you just do 4 factorial in this case. But here with free, that's not the same. It doesn't matter which E is placed in a spot. At the end of the day, an E is placed in the spot, and that's all that matters. So you won't have quite as many arrangements because, for example, free is the same as free. And someone might say, well, the E's are swapped around. Well, you can't tell because it's still the same exact combination now. So you have to eliminate options like that. So what you do is you take the total number of different items, still 4 factorial, but what you have to do in order to reduce the number of options is divide. And you're going to divide by, since there are 2 E's, you'll do 2 factorial. And so you do 4 factorial divided by 2 factorial. And you can just type that in your calculator. You can also say, hey, remember what 4 factorial is? And remember what 2 factorial is. So we really have 4 times 3 is 12. Once again, typing in your calculator is the same thing. Or on the top you have 24 divided and then divided by 2 on the bottom. So example 7, how many distinguishable arrangements are there for the letters of the word Mississippi? So Mississippi is obviously a whole different animal where there's a lot of repeating things. So you have 11 letters total, including repeats. So then you say, okay, I's. I's repeat 1, 2, 3, 4 times. So for the I's, you do 4 factorial. Then you have to go through the same thing for the S's. Another 4 factorial on the bottom. And then for the P's, you have to do another 2 factorial. And so what happens here is each time you have a letter repeated, you have to do factorial, divide by a factorial for that letter. And it's important that if you're typing this in your calculator, you put parentheses around the bottom. So you take 11 factorial divided by all of that, and you would end up getting 34,650 different combinations, which if you just compare that to 11 factorial, is quite a lot smaller. I want you to try number 8. So number 8, when we're trying to find zip codes or combinations of the zip code for arrangement, or excuse me, for anchorage, not arrangement, you would say, okay, there's 5 spots total. There's 2 9s and there's 2 2s. So you take 5 factorial divided by 2 factorial and another 2 factorial, one for the 9s, one for the 2s. And you'd end up getting 30 different combinations or different arrangements you could have. All right, so now these are going to be more probability examples that you would specifically see on tests like the ACT. So example 9, a box contains 8 nickels, 10 dimes, 14 pennies, 3 quarters. What's the probability of randomly selecting the following? So first, let's total up the number of coins in general. So if we figure out, okay, how many coins are there in total? There's 35 total coins. That's one of the first things you want to do. Now, what's the probability of selecting 1 dime? Well, take the number of dimes divided by the number of total coins. 10 out of 35. That reduces to 2 over 7 if we reduce the top and the bottom by 5. Want me to try B and C? B, a coin that's not a dime. Well, if there's 10 coins that are dimes, there's 25 that aren't. You could either find that by taking 35 minus the 10, because if either a coin is either, a dime or not a dime. It can't be both. Or you could add 8, 14, and 3 for the nickels, pennies, quarters. And 25 divided by 5, that would reduce to 5/7, which, as you notice, adds with 2/7 to get 1, just like 10 and 25/35 did. So a coin that is not a quarter or a penny. So quarters and pennies make up 17 of them, and nickels and dimes make up the other 18. So we want 18 out of those 35, and this doesn't reduce at all. All right, a set of numbers consists of all odd integers greater than 3 and less than 20. What's the probability that a number picked at random from the set will be? So let's first of all figure out all of the sample space here. So the odd integers greater than 3 and less than 20. So you're talking about 5, 7, 9, 11, 13, 15, 17, and 19. Because we can't include 3 because it has to be greater than 3, and can't include 20 because not only does it have to be less, but 20 is not odd. And integers just means that it's a non-decimal or a fraction. So what's the odds that it's divisible by 3? So how many total numbers are there that we're selecting from? There are 9. Excuse me, try that again. There are 8. So how many are divisible by 3? Well, you got 9 and you got 15. So 2 of these 8, aka a fourth of them are. Now, what's the odds that you get a prime one? Well, 5's prime, 7 prime, 11 prime, 13's prime, 17's prime, and 19's prime. So a lot of these are prime, and as a matter of fact, 6 of them. So you have 6 out of 8 are prime. And that would give you 3 out of 4. Now you might notice, I should say, that 2 8s and 6 8s add up to 1. This is just like 1/4 and 3/4 do. Now that doesn't necessarily mean the same correlation here, to where a coin can either be a dime or not a dime. It's not that a number can either be divisible by 3 or prime, one or the other, because there's numbers that are not divisible by 3, such as 4, that still are not prime. But in this sample size, it happens to be that because they're all odd integers, that if 3 doesn't go into any of these in this scenario, that it was prime. But that won't always be the case. All right, what are the odds that it's a perfect square? So look at here and we say, okay, how many perfect squares we got? We have quite literally 1. So you say 1 out of 8. Call it good. Now its probability good is an even number. We might notice there's no even numbers. So 0 out of 8, aka 0, is the probability. So the probability that an event happens is 1/4. So what's the probability it doesn't happen? Well, if it happens 25% of the time or a fourth of the time, it doesn't happen the other 3/4 or 75%. And how you would find that mathematically speaking is you would take 1 and subtract how often it happens. So 1 minus 1/4. And you say, well, 1 is 1 over 1. And that'd become 4/4 minus 1/4 when you get common denominators, which would give you 3/4. 12. A bag contains colored marbles, red, black, and white. There are 10 red marbles, 8 black marbles. The probability of pulling out a red marble is 1/3. How many white marbles are in the bag? All right, so here we know that there are 10 red marbles, and we know only how many red and black there are, but not how many white. So you'd put 10 over however many total marbles there are to give you 1/3 the probability of pulling it out. Now we don't know how many total there are, but we know you would add 10, the red, plus 8, the black, and let's call X the number of white marbles. That's what you would do. If you knew X, if you knew the number of white marbles, you'd add it with 10 and 8, and you'd put it on the bottom of that fraction, and that would reduce to 1/3. So let's set it up this way. And now, we know that since this equation would be true if we knew what X was, it must be true even if we don't know what X is. So we cross multiply here. So you take 3 times 10 and get 30, and 1 times all of that to just get 10 plus 8 plus X. Now, if it was a number other than 1, you would need to distribute. So here we'll combine like terms and get 30 equals 18 plus x. Subtracting 18 tells us the number of white marbles is 12. So there are 12 white marbles. And if you want, you could always check your work of saying 10 and then divide by 10 plus 8 plus 12, aka 30. Does that reduce to 1/3? Yes, it does. A bag contains 6 green marbles, 10 blue marbles, 14 red marbles. How many additional green marbles must be added to the 30 marbles already in the bag so the probability of randomly drawing green marbles is 1/3? I'm going to try this one. So here, we're going to have 6 green marbles plus however many we're going to add over the total number of marbles already in the bag, 30, plus the same number of green marbles we're going to add is going to be equal to 1/3. So you'll cross multiply. You do 3 times 6 and 3 times x to get 18 plus 3x. 1 times 30 is 30, and 1 times x is x. I'm going to subtract x from each side and get 2x. Subtract 18 from both sides and get 12. I'm now going to divide both sides by 2 and get x equals, try to not get not 11, but 6. So you would need to add 6 green marbles. All right, that is all for today for Algebra 2, Section 9.3.